Okay, so we've plotted the point. Did they say what this is? Is this? Oh, it's a differentiable function.
Yeah.
So again, this is the function itself. That's good to know. Not the derivative or anything like that. Okay, so in calculus, the derivative has many interpretations. One of the most important interpretations is that the derivative is rate of change. We know that. We've said that a billion times. When speaking of rate of change, there are two rates of change that can be found that are associated with a function. What we call average rate of change and what we call instantaneous rate of change. So, back in 9th grade, when you first start talking about slope, you talk about slope in reference to what particular function?
Linear.
Linear. And what is special about linear functions? They're constant. So the average rate of change over a linear function and the instantaneous rate of change are exactly the same. But if you think about throwing a ball up in the air, the rate of change, or the rate at which the ball is traveling, is it the same speed the entire time, from the time it leaves your hand to the time it comes back to your hand? No. So we could calculate the average by taking how many seconds the ball hung in the air, or how long it took for the ball to go from your hand and back down to your hand, and calculate the average speed, or the average rate of change. Or then we could say, at exactly the height 3 centimeters from your hand, what speed was it traveling at that moment? And that would be instantaneous rate of change. And that's where calculus is pretty important. You could have. Yeah, you could have. Like, there's a long way to do things, and then there's the shorter way. Okay, so average rate of change on an interval. So this is important on an interval. So we talked about intervals the other day when we were talking about extreme value theorem, about closing things off on an interval. Average rate of change will be found by slope of a secant line. So we're going to say on an interval, a closed interval, A to B, where A and B are numbers.
I wrote different things.
Change is just going to be found by using the slope formula. Now, what you do have to make note of is when you are told an interval, A to B, which value are they giving you, X or Y? When you're given an interval.
Oh, they give you X.
It's always the X value, which means you might have to calculate the Y value. Now, the one we just got, we don't have to do that because they gave us the table. But you're always, when you're given an interval, given the X value. But when you're looking for rate of change, we're going to need the Y values as well. We're going to need a completed ordered pair, which you won't be given just over the interval all the time. So, instantaneous rate of change is slope of a tangent line.
So is it just slope of the derivative?
It's just the derivative.
Oh, okay.
So we know this?
See, that's going to start messing me up if we start learning new stuff, but it's stuff we already know. But they're calling it something else.
Okay, so it all, I think when we look at it graphically, I think it all begins to make perfect sense. Why one of them is just the average rate of change, where one of them is instantaneous rate of change. So down at the bottom it says find the average rate of change on f of x, that's the one we drew, on the interval 2 to 12. So those are my two x values. So I'm going to go up on my graph and I am going to put a dot on the function at 2. There's already one, but I'm going to put another one. At 2 and at 12. And I am going to draw a secant line because I am looking for the average rate of change, which is defined by a secant line. Y'all remember secant lines from geometry pass through a figure, whereas tangent lines just touch one time. Okay, so there's my secant line. And I am just going to calculate the slope of that line. Now, of course, I just drew it, so I could just count it. But I am going to use the formula and the points. So my ordered pair for 2 is the ordered pair 2, 5. For 12, it's 12, 8. Plug it into the formula. 5 minus 8 over 2 minus 12
3 over 10.
is 3 over 10. That's the average rate of change. I can go up and count it and just see if that's right. Rise over run. 1, 2, 3. 2, 4. Voila. That's beautiful.
So, like 11.
Okay, so now if you think about it, before we actually do the instantaneous rate of change, if you think about it, that is finding the average speed on this portion of the circle, because that's between 2 and 12. So I'm figuring out the average rate of change. So if I wanted to get more accurate, let's say I think they're going to tell us at 4. Yeah. They want us to find the instantaneous rate of change that happens right here. So how fast is it going right there? Well, if you want to get more and more accurate, you would just take these points and move closer to the point that you want, right?
Yeah.
Every line that I draw is a little bit closer to that one. So you just take your secant line, and instead of it being secant, you take these two things and you get them to approach each other, which is where limits come from, why derivatives are limits. And I get them on that 4, or the tangent lines. So, is the instantaneous rate of change at x equals 4 greater than the rate of change at x equals 6, or less than the rate of change at x
So
equals
are we
6?
just taking the derivative and plugging in 4?
Well, you would be taking the derivative, but even before you
Yes.
answer, let's make it, even before we take the derivative, let's just look at it and you tell me,
This is great.
based on
4 is great.
the picture of the graph,
Oh, wait. Maybe that.
is your slope at 4 going to be greater than the slope, the orange line, or less than?
Well,
Just
if
by
I
looking.
I think
the
greater.
orange line.
Because this thing is going to a peak.
Okay,
I
so
think
let's,
that's it.
What?
Because whenever it's peaking, it's slowing down. So it's
okay, so I'm going to go to x equals 4, and I'm going to draw a tangent line.
She threw an orange line and made no sense to me.
The orange line's a secant line.
Yeah, but we're not talking about
Yeah,
we're talking about the slope at 4.
It just said, this question just says, is it greater than the rate of change at x equals 6? Oh, at x equals 6, it didn't ask me about this. You're right, never mind, I'm sorry. Okay, so wait, I'm going to draw, I drew one, I'm sorry, I thought it was comparing the two. Okay, so I drew one at x equals 4, so let's draw one at x equals 6.
Okay. Yeah. 4 better.
Four's great.
4 much more better.
Why?
Because
In terms of the picture.
Because the 4
Because
more
it's a
slope.
steeper line.
Because it's a steeper line, right? 4 is a steeper line than 6.
Yes.
So the derivative at 4 is greater than the derivative at 6. Or the instantaneous rate of change at 4 is greater than the instantaneous rate of change at 6 because the tangent line Now think about it in terms of what we were just talking about, throwing a ball in the air. Why would the instantaneous rate of change at 4 be greater than the rate of change at 6? What's happening at 6?
Because it's reaching its
peak, and it's gonna stop and
At
have zero rate of
Gravity's have
change.
less amount of
It
time
be
to
slowed down
affect.
by that gravity.
Gravity's pulling it in.
So what happens at, in this case, the peak appears to be at 8. Is that where the peak is? What happens at 8?
There's no rate of change.
But,
It's-
it
it's
stops
max.
and starts falling.
It stops and
Like that.
it stops and it changes direction.
XD.
So my point at 6 is getting closer to that place where it stops. And you can actually see that when people throw a ball, if you're paying their
Oh, you're
attention,
right.
you can actually see
Mr.
it.
Lewis did it.
I have one somewhere.
You said
Okay.
it was so good.
Throw it at
It's like,
close
look.
to space and let's see it stop.
That's a little different. Okay, Rolle's theorem. It's a little different.
Rolls.
Rolls.
Roly-poly thing.
This was like a big box for a reason.
Actually, this big box doesn't need to quite be as big as it is.
XD.
But that doesn't give you permission to write huge, because then you'll run out of room.
They always give us big boxes when we don't need them.
They do. I agree.
And I bet you those boxes down there aren't big enough.
Yeah, the one on the left's probably not.
What a time to be alive.
I hate to leave it to you, this really bugs me.
Yeah, it didn't bug me until now, though. Thank you. That is so dainty, the metal continues bugs me. Like Stevie, you fly.
It's like the ability
XD.
Chelsea, we do it.
to see the shell.
I hate the word guaranteed, I've never spelled it.
It is a weird word.
Oh, that weird.
I think it always looks weird.
The continuous doesn't.
Continuous is spelled exactly how it sounds like it would be.
Right, okay. Yeah, keep it up. You cherry this one in my point.
Lisa.
Okay. So we're going to talk through this definition real quick. I'm going to ask you a couple of questions, see if you can figure out why. Okay, so first of all, it says if f of x is continuous on the interval AB. Specifically, what kind of interval?
Closed.
A closed interval, because I've got brackets.
I can't.
So we've got to be continuous on the closed interval, differentiable on.
The
Open
open
intervals.
intervals.
Now, why is that? Why would they say that the intervals at the end have to be differentiable?
I don't know, because it's gross.
If
Because
you
they were
if you
included.
close an interval, what does that create at the end of the endpoints? And are endpoints differentiable?
No.
Yeah.
So they're just saying if we didn't close off the ends, they would still be differentiable. Does that make sense?
Yes.
Okay, so that's why the second AB has parentheses and not brackets. And f of A equals f of B. What does that mean?
Then immediately the same.
That they're at the same, what is it? F,
Y value?
they're at the same Y value. So your two endpoints are at the same place.
That
Okay.
doesn't sound fun.
Because A is the beginning of our function. It's on the X axis, it's over here. And B is on the other end, and they're saying the two Y values are at the same place. Then there is guaranteed to exist a value of C somewhere on the interval such that the derivative of C equals 0. If the derivative of C equals 0, what does that mean?
Max for me.
There's a max or a min. Now think about that for just a minute. It makes perfect sense if I have a derivative, if I have a function that goes between these 2 points, somewhere along that way, it has a maximum or a minimum. It would have to be like in there somewhere doing something. So that's all that Rolle's theorem says. So let's look at this. Consider the function f of x on the previous page.
It can't be because.
Does Rolle's theorem apply on the following intervals? Explain why or why not. So let's look, I'll put my, hey y'all, I'm going to put my function up, and you're going to tell me whether Rolle's theorem applies to the interval 2 and 14 on this function. Does Rolle's theorem apply?
Yeah.
Yeah.
Is it continuous?
Yes.
Yeah.
Is it differentiable?
Yeah.
Yes.
Are my f of a and my f of b equal
Yes.
to one another on the interval 2 and 14?
Yes.
Yes.
Because here's 2, it's 2, 5, and 14 is 14, 5.
Yes.
So Rolle's theorem does apply on the interval 2 and 14.
And when it says explain, can I put because it matches all of the reasons above?
Yes, that's what I was gonna put.
It's probably quicker to just say continuous differentiable and f of a equals f of 2 equals f of 14. Because you have symbols for all that.
No. I don't know those.
Yeah, no, I don't know.
I know I can do symbols for the f of 2 equals the f of 14 part. That's about it.
What about if you because we have to say that there's a value that
We're about to, yeah. But first of all, I'm just explaining why does it apply. So now, where is, because it says if Rolle's theorem applies, then there is guaranteed an x value, they call it c, where the derivative is 0.
Me?
So if we put dy, we're gonna f equals 0 at.
Yeah, you could. I just put the f prime of 8 equals 0.
But then the next one does not work.
The next one does not work.
xd
Okay, so on the interval 2 to 8, Rolle's theorem does not apply.
Because f of a
Because
does
it's
not
not
equal
a.
b.
Because f of 2 does not equal f of 8.
And on the closed interval, that endpoint would be differentiable, would it? Which is okay.
Which one?
F of 8. Because it's like,
Surely that's still theory. We can break it.
or do we just need to disprove it with like one thing?
Just one thing.
Oh, okay.
One thing's enough.
So dividing this one, go ahead and
Okay, so now we need to determine whether or not Rolle's theorem is applicable or not to the following functions without a graph of them. So this is where knowledge of all of your parent functions, etc., comes into play. On 1, is g of x a continuous function? What is it? It's not in a great order, but what is it?
It's a continuous function.
It is a continuous function. It's
No.
quartic. It's quartic. I mean, it's in the wrong order, but it is quartic. It happens to be upside down quartic. A regular quartic looks like a W, right? But that would be negative, so it's upside down. So it's an upside down quartic, so it is continuous. Is it differentiable?
Amazing.
Yeah. So now the only other thing we need to know is on the interval, is g of -3 equal to g of 0?
Well, we're gonna plug it in.
Let's
front
find
there.
out and see.
XD.
So
6 times.
Yeah.
81. Please tell me something.
So it equals 0, doesn't it?
Yes, it does.
XD.
And g of 0 obviously equals 0. So
Yes, I do. This is gonna be really disgusting for you. This is not that
okay, so Rolle's theorem applies. I probably should write as continuous and differentiable.
I just wrote up in the corner, like I wrote continuous and differentiable, and I put like check marks next to them.
That's good. Okay, so now, because of that, we want to find that place, that value of c, where the derivative, bless you, equals 0.
Get the derivative solve.
Get the derivative, solve for 0. So I'm going to find my derivative. And then set it equal to 0 and solve.
Not again.
GCF of 2x.
Are we gonna use a fraction?
2x equals 0.
Not today.
This is not big.
I just told you.
It's so saying.
The square root of 9/3.
So it's gonna be,
Yeah.
square root of 9 over 2.
Which ends up being the square root of, because they don't, I don't know why, because they don't make you rationalize. But the 9 is a perfect square, so the top can come out. So it ends up being, don't forget, when you take square root, you got two answers, positive and negative. Okay, so, 0 doesn't count. Why?
Because
It's
it's
included on the interval.
Because it's included on the interval. And remember, my theorem says there exists a value of c on the not included interval. So if you're looking at the theorem, your value of c that you're looking for, it can't be an interval. It has to be in between the two things. So the 0 doesn't count. It's not that there's not a max there. There probably is, or a min, but
So, that's there's 2?
yeah, oh yeah.
Okay.
Yeah, yeah, so this one doesn't count, and then, so then I have 2 that do count. Now, you do have to make sure they're on the interval, but they are, because 3 over the square root of 2 is between -3 and 0, so it's the negative version.
Okay, alright.
It's smaller than
XD.
8. Alright, y'all ready?
I'm still ready.
Okay, first of all, you have to, in your mind, figure out what kind of function this might potentially be, whether or not it is continuous and differentiable. Now, we got a huge issue with this.
not continuous.
It is not continuous at
X equals -2.
x equals -2.
Yeah, that's all the thing, so we can't do it.
Can't do it.
Can't do it.
Can't do
So
it.
it's not,
We can't do this.
we gotta explain to them. It will not work.
That was quick.
In a day and an age.
So Rolle's theorem does not apply because g of x is not continuous at x equals -2, which is on the interval. So, everybody okay? So far, so good?
So far, so good.
This is pretty easy.
So good, Dad.
All right, Rolle's theorem guarantees that if a function is continuous on the closed interval,
Of mean function.
differentiable on the open interval, and f of a equals f of b, then there's guaranteed to exist a value of c where the instantaneous rate of change is equal to 0. Then there is the mean value. Okay, so we did the other day, last week, extreme value theorem. An extreme value theorem found absolute maximums and minimums. They could be somewhere along, or they could be on the end points of a closed interval. Now we've just done Rolle's theorem. Your end points have to be at the same height for Rolle's theorem to work, and if Rolle's theorem, if it applies, then all it says is that there is some place where there is an instantaneous rate of change of 0. And now this is mean value theorem. The mean value theorem is very similar to Rolle's theorem. In fact, Rolle's theorem is a specific case of mean value theorem. It just says, make sure I get it.
Means all the game.
So it's f of a have trouble with continuous. Thanks a lot, Gavin. Now I messed up. That's okay.
So I always shorten it, I just wait to see what needs to be.
What if she never, like, doesn't listen again?
Now I'm gonna miss it all the time.
It's not your fault, I'm gonna divide by 0.
I'm gonna come back in like 10 years and I'll still be missing it up.
Come back in 10 weeks, I'll show you my organic and
You're gonna come back in 10 years and show me all about dividing by zero.
then you're gonna be like, I can't use this part, see what?
Well, no, we'll just have to put it in a big book somewhere and she'll find out anyways.
Because then I'm just gonna change the face of math class, so if you can divide by 0, then math is changed forever.
So
Of course
true.
it is.
Well, it's not defined anymore. Yeah, it's just.
It's Gavin's, it's the theorem of Gavin. Only guaranteed, and I don't know Gavin.
It already exists. That's those anthologies.
Oh yeah, we're both. We'll do it.
One is anthology.
I like cardiologist myself.
Okay, so the mean value theorem says if f of x is continuous on the closed interval a to b and differentiable on a to b, then there is guaranteed to exist a value on the interval of c such that the derivative, or the instantaneous rate of change, equals the average rate of change. So, because remember that's what we did at the very beginning. This, which is just the slope formula, represents average rate of change. The derivative is instantaneous rate of change. Okay, so here we go. We're going to consider the function that they've given us.
Consider the following.
And the graph of it is pictured below. Does the mean value theorem apply on the interval of -1 to 5?
No.
Why not?
Because it's not a graph at negative 1.
Because there's no graph at -1. Because this particular graph has an asymptote at 0. So h of x is not continuous.
I feel like the whole little graph not working thing is not gonna happen.
Yeah, probably not. But it does happen, so you have to make sure you don't waste time trying to do it
A 1
when it
in
won't
10
work.
chance that there will be a graph that doesn't work.
The mean value theorem.
It's the meaning.
It doesn't apply on the interval -1 to 5. But does it apply on the interval 1 to 5?
Yes.
No. The function is both continuous and differentiable. Alright, so graphically, what does the MVT guarantee for the function on the interval? They want us to draw this line on the graph. So all it's saying is there is a place where the derivative or the instantaneous rate of change is going to equal the average rate of change. Now remember, the average rate of change was a secant line. So let's draw the secant line on the interval 1 and 5. So there's 1, 5.
Alright, that's one. So now we'll take the derivative of
So
our
that
original.
is the average rate of change on the interval 1 to 5. So there is, because they asked us to do it graphically, there is a place where the instantaneous rate of change is equal to the average rate of change. Which means the slope of the two is the same. So I am just looking for a line that is tangent but has that same slope.
Oh, so do we find the derivative?
You know, we're just doing it graphically right now. I am just going to
Okay.
draw a parallel line,
Oh.
because that would mean they have same slopes, right? Now you understand why you spent all those years going, parallel lines have the same slope.
No.
because now that means my instantaneous rate of change and my average rate of change have the same slope. They're parallel lines.
So it's somewhere in between.
So it looks to be, yeah, it's a little in between. It looks to be right about here somewhere. A little more than 2 maybe?
Yeah.
Okay, so now we'll actually calculate it and see what it is. So, my graph, I'm looking for the instantaneous rate of change. So I'm going to find the derivative. Well, I'm going to write this as h of x equals 3 minus 5 to the x minus 1. Is that be okay? Just rewriting my in polynomial form makes it a little easier to take the derivative. So now it's 5 over x minus 2. Or x. Okay, so that's my derivative. Now, I need to figure out what it equals. It equals the average rate of change on the interval 1 to 5. So my average, so 1 is the ordered pair 1, negative 2, and 5 is the ordered pair 5, 2.
Okay.
So I'm going to do negative 2 minus 2 over 1 minus 5.
Okay.
So I'm, in red, I'm calculating the, did I do it wrong? Oh, this is negative. So it comes out to be positive 1. So this is my average rate of change. So now what I want to know is where does my derivative equal 1? So I'm just going to set the two things equal. You know what, I just realized this isn't a half. It's not square root. It's, that was dumb.
Okay.
I should have done it. Sorry, I should have done it.
Okey-dokey.
Hey.
Why didn't you? You should have.
Yeah, I didn't look at
No,
it.
I just thought I was doing something stupid.
Okay, so now I'm looking for where my derivative, which is 5 over x squared, equals 1.
Square root of 5.
So yes, it's square root of 5.
XD.
So x equals both positive and negative square root of 5, which let's see graphically because I just want to know if graphically how close we are. Oh, I guess it's just the positive version. We're on the interval.
Yeah.
So square root of 5. Oh, it's 2.23.
Old people calculate. Well,
It's like,
I don't know where my other one is.
that'd be pretty cool.
that's young stuff.
So that is pretty close to what we got
I
graphically.
understand those.
Yeah, those are nice ones, the big buttons.
No, they're not.
I like them.
Yeah.
Not for calculus.
I still miss
I
them.
love looking at the second derivative and doing it.
I know, and it does it fast. These-
Yeah, I still don't remember how to do it, so.
All right,
That's on probably close.
explain why you cannot, okay, why can we not apply, why can we not apply the mean value theorem for this particular function? Now, anybody off the top of their head, without putting it in your calculator, tell me what that function looks like?
Oh,
Yeah.
it's a radical.
Okay, except for it's cubic. So yes, it's a radical, but it's not just a square root, which would go just this way. But remember, cube roots can go both ways because they can be negative. So it looks like
Oh, yes.
it's a
The
bird.
bird.
It's a bird. So why is the mean value theorem not apply to the bird?
Because it would be non.
It's non-differentiable where?
At the, oh,
At the cusp.
XD.
And in this case, that cusp is at 0 because of where the radical is. So it's non-differentiable at the cusp, so mean value theorem doesn't apply. And that- That's it. So I guess we should say that.
Wasn't even worried about it.
I could've killed you.
I did them.
That just what x means, kind of x equals 0.
Alright, next.
Stand.
Find the equation of the tangent line to the graph at f of x equals 2x plus sine x plus 1 on the interval 0 to pi at the point which is guaranteed by the mean value theorem. Now they didn't ask us if mean value theorem applied, they just told you that it did. So they want you to find the place on the interval from 0 to pi where the mean value theorem guarantees there to be a point. So what do I need to do first?
Find the average.
We do need to find, even before that probably. I'm going to take the derivative first.
Yeah, props. I like that one. I like that one.
And then I would find my two ordered pairs. You need your two ordered pairs in order to find the average.
I like to pick 0 and pi.
Smells like tomorrow.
Yeah, there's no.
Oh, yeah, I see what we have to do. I'll show you on top. I thought they didn't get it.
It doesn't matter, no one got the joke.
Oh, wait. Shenanigans.
Oh yeah, that was like totally video recording the whole time.
What hit?
We were being,
What was that? We're being recorded.
we were.
And we just fly across the screen. Whee!
Terry,
What?
Take it, Michael.
What?
BJ's desk is gone.